Hello everybody, welcome to Unit 2, Chapter 6, User-Defined Functions. And in this chapter we're going to introduce structured design and discuss how to design and build a program in multiple functional modules. We'll explain the difference between value parameters and reference parameters and how the scope of a variable affects its value during execution. We'll also learn how to write functions with default parameter values as well. And of course, our learning objectives are in line with all those things that I just listed. Before we start, we need to explain the names of some library header files. Because C++ is built on top of C, it uses C's library files. The header files for those C libraries are called something.h, like math.h for the math functions, and ctype.h for character-related functions. C++ wraps those headers in C++ style header files, and it's called C something. That's why we have C math and C type. So the C string header file is actually string.h from C and contains functions for C strings. And the string header file is for the C++ string class that we've been using. And then we'll explain C strings and strings in the next unit, Unit 3. Chapter 6 explains how to build a program based on structured design. In structured design, we break a problem down into smaller subproblems. Each subproblem is then solved using structured design, and the solutions are combined to solve the original problem. The program will be composed of a collection of functions. And this is a little bit different from what you've learned with object-oriented programming. Structured design is also known as procedural design, top-down design, or stepwise refinement. While these methodologies can also be applied to object-oriented programming, it's critical to understand that there's a difference between procedural design and thinking in terms of objects, which we're not really concerned about right now. No matter how you approach a programming problem, you should always design the algorithm first. You need to spend sufficient amount of time thinking about your program before you actually set down to write any code. Due to the way that C++ compiles, if we want to introduce user-defined functions into our main program, the main function must first understand what the function definition is. A single file program is typically structured much like what you see here. First, we have our include statements. This brings in any additional header files that we're going to use. Then this is followed by our function prototype. Then by our main function. And then finally any function definitions that were declared above. A function declaration or prototype is a function heading with a semicolon. The compiler needs this semicolon to know that the end of the declaration has been reached. The definition of a function, also called the function implementation, is the heading plus the function body in braces. Note that there's no semicolon after the heading, as there still is a body of the function, as you can see here. Right here. Okay, we got a body. Up here we have no body, but a semicolon. So you might be asking yourself, this seems like a duplication of effort. Why do we need function prototypes? Well, the compiler compiles our source code file sequentially from top to bottom. When it encounters a function call, the compiler needs to know that there exists such a function with matching number and types of parameters and the return type. Otherwise, the compilation would fail. That's why we put function prototypes before main in any other function definitions. And this is a coding convention that's used in industry. So to summarize, programs are compiled sequentially, and function prototypes appear before function definitions, so the compiler compiles these first. Okay, then the compiler can correctly translate a function call. And you can see examples of this in your textbook on page 375. It should be pointed out that for simple programs, it is possible to place the function definition above the main method and omit the declaration like this. Be advised, however, that it may not work when there's recursive definitions, and is generally not used in formal software development. Therefore, we won't be using it or using this structure in this course. We'll only be using the previous structure like this, like that. Another concept that we need to discuss is parameter names, specifically formal parameters and actual parameters. We differentiate formal parameters from actual parameters by the fact that a formal parameter is the variable defined in the heading of a function prototype or definition, while an actual parameter is the variable used in a function call, or the value that is passed into the corresponding formal parameter. For example, here the actual parameter 1 or 2 will be passed into the formal parameter x and y when it's called. When a function is called, memory for its formal parameters and local variables is allocated in the data area for that function, and this is known as a stack frame. For a value parameter, the actual parameter's value is copied into the formal parameter's memory cell. Changes to the formal parameter do not affect the actual parameter, as the formal parameter is just a copy of the actual parameter. So you can see here in our main function, we called function and took x, y as parameters, and we copied in 3 and 4. So we passed in a is 3 and b is 4 into x and y, and so now x is equal to 3 and y is equal to 4. So if we change the values of x and y, these are not going to change the values of a and b. And of course, local var 1 and local var 2 are just memory locations that are used within the function. Okay. For a reference parameter, on the other hand, the actual parameter's address is passed into the formal parameter. Note the ampersand on our formal parameter in the function declaration. Therefore, both formal and actual parameters refer to the same memory location. That is, they are referencing the same variable. Because of that, whatever happens inside of a function to the formal parameter affects the actual parameter. So we passed a and b into the function just like before, but because we're using the reference operator here on x and y, now x and y is equal to the memory location of where that value is stored. So when we change x, it's actually changing the value that a holds. So if we set x equal to 4, now a is going to be equal to 4. Okay? And this is something that's kind of new to you if you have never seen this before. And we're going to talk much more in depth about this later when we cover pointers and reference operators and all this and that. So this is just kind of a preliminary heads up to what's coming. Software developers often document the types of parameters through inline software documentation. This is known as the modes of the parameters. An in-type parameter only passes a value into the function. In means data flows into the function via this parameter. Such a parameter must have been initialized before going into the function, and it should not be modified in the function. Pass by value parameters will always be in-type parameters because the compiler doesn't allow you to actually change the values. Remember, the values are copied over. An out type parameter only brings a result back from the function to the caller. Out means that data flows out of the function via this parameter. It doesn't matter that this parameter has been initialized or not. Even if it has an initial value, that value will not be used as its out only. An out type parameter has to be implemented as a reference parameter. An in-out type parameter does both, passing an initial value in and bringing back a modified value. an in-out type parameter needs to be implemented as a reference type parameter as well. Take a look at this example. You can see that we have three parameters, x, y, and z, and x is implemented as a value parameter, right? It's no reference sign there, it's just we're passing it in by pass by value, right? So even though x receives a value in the function, this doesn't affect the actual parameter because of it being passed by value, and therefore x won't be able to pass anything out as a result. The compiler won't let us, right? So x, it has to be an in type, right? As evident by our inline comment right there, right? Y and z are implemented as references, right? They're reference parameters, so they must be either out or in-out. And you can see that y's first occurrence in the function right here, right, is to receive a value. Therefore, at this point, it's an out type, right? We know that we're changing the value, and we're going to be returning it once the function is done, okay? Z's first occurrence on the right-hand side of this expression is to provide its existing value. So here you can see that the first time we use z, it hasn't been initialized in our function. So we know that z has to be an in, at least, okay? When the function call ends, right, we can see that z has been assigned a value, and its values has been calculated by x and y, okay? So we know that z has both been used as part of a calculation, and it's also been used as an output because we're not doing anything else with it at this point. So z is an in-out. So you might be asking yourself, well, y is being used as both as a assignment and as part of a calculation. Why is y not an in-out? Well, that's because the value of y is established inside of the function, right? We're not using the value of y initially to calculate something else. The first time y has a value is when we calculate something and store it as a result. So therefore, y has to be an out. Even if we use it for subsequent calculations within this function, y is still just an output variable because its previous value has no impact on the rest of this function. Okay, so there is no in coming in via the y. Even if it has a value, before we use it on the right hand side, we are assigning it, in this case, w mod 2, and then we're using that value. Okay, so that's why y is an out and z is an in out, because we are using z before we assign it a value. Take a look at the following function. Which of the following is the correct mode of parameters documentation? Pause the video and think about each variable and how it's being used. Okay, last chance to pause it. I'm going to reveal the answer. If you chose answer C, you got it right. Both speed and time are only used to calculate distance, so they are input variables. Distance isn't used at all except for the assignment of its value, so it's an output value. You can see that right here, right? And C is used both for a calculation, right here, okay, we're casting it to number, right? And it's also used as an output, right? You can see right here, we're assigning it a value. So it's both an input and output. So why does all this in-out stuff matter? Well, it helps us pick the proper parameter type and implementation when we're talking about structured design. Here are some general design guidelines when working with functions. If we need to pass out a single value from a function, set its return type and use the return statement. If we need to pass out multiple values, set its return type to void and use multiple reference parameters. Another possible design is to have one value from the return and the rest through reference parameters. And if we need one single parameter to both send in a value and pass out a value, then you're going to use a reference parameter. Software developers also document pre and post conditions of a function. It's often kept with the function specification. A precondition specifies what should be satisfied before the function starts, like a prerequisite. A precondition describes if the parameter should have been initialized or should hold a specific value or value ranges. A postcondition specifies what should have happened when the function ends. It should describe any modifications on the reference parameters, the value returned, and even runtime exceptions that may be thrown. In this example, given the calculate change function, its preconditions may be written as that total and coin value should have been initialized, and total holds a non-negative value, and value coin holds a positive value. As evident by here, you can see that coin value must be greater than 0, and total must be greater than or equal to 0. Its postcondition would be that total will be updated to the total after taking out as many possible coins of the given coin value and still hold a non-negative value by the end of the function. You can see that in our postcondition, right? Total is going to be equal to total minus the max number of coins times the coin value, and total will be greater than or equal to 0 when we're done. Together, the pre and post conditions should help you understand better what the function does. When you're thinking about the structure of your program, you also need to think about the lifetime or the scope of the identifiers that you will be using. The scope of the identifier determines where in the program that identifier is accessible. Okay, so here you can see we've got two variables, num and number, and a function called function. Local identifiers are declared within a function. It can be used in its function after the declaration. So here you can see the scope of number is inside of the function. And we can use number as soon as we declare it. Okay. Global identifiers are identifiers declared outside of any function. The variable num in this segment of code is a global variable. Okay. And it can be used any place in the program after its declaration. So here you can see the scope of number. All right, and assume that this stretches on to the end of the program. Don't use global variables if local works. Okay, we assign the smallest scope to a variable that it needs to get the job done. Under the same principle, if we were talking about, say, like a database, we wouldn't give every employee access to the human resources database, right? We don't want you seeing the salary of your coworker or what insurance plans they've picked and blah blah blah, right? We use the smallest access possible, and this applies to variables just as it would in the security world. When we have a larger scope that encloses a smaller scope and they each declare a variable with the same name, variable shadowing will occur. Okay? So let's take a look at this segment of code again, except for notice how now the number, we've changed the variable num to num. So we've got a global num and a local num. Okay? This means that when you use num inside the function, it's going to assume you mean the local variant, not the global num, right? If you want to use the global num, then you need to use the scope resolution operator in front of it, just like this, okay? The double colon, right? This tells the compiler, hey, I mean to use the global num variable, okay? The reason local variables are available only inside of a function while a global variable can be used in any function is because their memory space is handled differently. Memory space for local variables and block variables are allocated at the beginning of a function or block and destroyed at the end of that function or block. When you call a function again, its local and block variables will be created again. So these are also known as automatic variables. Global variables, on the other hand, are allocated only once when they are declared, and they remain alive until the end of program execution. And these are also known as static variables. You can declare a static variable inside of a block by using the static keyword. So static, whatever the type is, and then the identifier that you give it. So static int x, right? And here's how we would declare it in code, right? So static int x, static int y equals 0, right? We are initializing it in its declaration. The C++ standard doesn't specify that global and static variables should be initialized automatically when declared. Some compilers automatically initialize them to 0 for that type, and some don't. So bottom line is that you need to make sure that you initialize it every time. Don't depend on the compiler to do it, okay? Because each compiler's compiles things differently. So just get in the habit of always initializing a value to some kind of null value. And that goes for any language and anything. It's always a good idea to initialize your variables as soon as you can. The benefit of static variables are that they can only be accessed inside of a function, but they retain their value between function calls. So a static variable therefore would be appropriate if it should be used by one function and one function only, but you need to make sure that that value stays there in between each call, just like I said. So this is much safer than using a global variable, which can be accessed anywhere and then can get modified. You're going to find yourself in situations where you're messing with a global variable in one spot and then you don't remember that, and then so you go to use it thinking it's going to have one value and it has a different variable, and it can get really messy really quickly. So static variables are a way to protect a variable and still use their value in between function calls, especially when we're not dealing with object-oriented methods, right? We're talking about functions here. We're not talking about methods and objects. Functions are standalone things, and so now we are giving them some kind of state. We are saying like, hey, I know I'm calling you, but maybe you want to keep track of how many times that function was called, right? So every time the function gets called, you just increment it, and at any point you could output the value of that variable as long as you're inside that function. Finally, let's take a look at function default parameters. Take a look at this following program. Can you figure out what it will print? Go ahead and pause the video now if you would like to try. We can specify a default value for a function parameter. When a function call doesn't specify a value for such a parameter, the compiler rewrites this function call and inserts the default value of that argument. Because of this, when the first call is made, here in box volume, the compiler, it's going to rewrite this as box volume 111. It's going to take our default values here and pass them into this function call. Okay? The second call is going to look like this, right? Because we have 10, so the compiler is going to fill in the last two parameters and so on and so forth. Okay? So you should see the final numbers printed out. It's going to be 1, 10, 50, and 100, right? 1 times 1 times 1 is, of course, 1. 10 times 1 times 1 is 10, so on and so forth. Be aware that default values should only be specified once in a function declaration. If you repeat them in a function definition, as we've done here, right, you can see we've got defaults listed here, and we've got defaults listed here, right? It will not compile, and it's going to give you this error right here. So you've redefined the default parameters. C++ requires that all default parameters must be the rightmost parameters of the function under discussion. Okay, so you can see here that this works, but this doesn't, because this width doesn't have a default value, but height does. So this is going to throw a compiler error. So this means once you define a parameter with a default value, anything after it has to have a default value as well. So since we had a default value for length, every parameter after it has to include a default value. Similarly, you may only skip the rightmost arguments in a function call. While this is valid in some languages like Visual Basic, we can't do this in C++. Okay? You can't just randomly decide to skip variables. The default value you specify for a parameter may be a constant, a global variable, or even a function call itself. A reference parameter can't have a default value because it needs to reference a memory location of a variable instead of just a value, right? So you can't say, well, I'm going to give you a default value, but this value is going to come from this location in memory. It doesn't work. All right. So in summary, we talked about how structured design works, how you take a problem and you break it up into individual pieces. And no, we didn't really show you any examples of that. We're going to do it in class, and throughout the whole course we're going to be doing this. But you need to understand it in theory, right? You take a problem and you break it down into smaller sub-problems until those are solved. Then you combine all those together to get your end result. We also explained the difference between a value parameter and a reference parameter, and we talked about how those can be in, out, and in-out parameter types. Okay, and this is something that we do in documentation as well to make it easier to read, so you can see what we're expecting these variables to do. And then we also talked about scope and how to use global, local, and static variables within your code appropriately. And then finally, we ended with how to use default values within function declarations, so that way you can, if you have a value that's going to be, most of the time it's going to be this value, then it's a good idea to include a default parameter value. So that's all for this lesson. We're going to go ahead and take a look at chapter 13 next.